What's up guys, Max Explained here. Today we're going to be talking about the physics of door hanging pull-up bars. So I've owned one of these door hanging pull-up bars for a long time, as is evident by it starting to fall apart. And although I've been curious about how they worked, I've never actually sat down and worked out the numbers for how they actually support my body weight. So I'm about 180 pounds, and the fact that the door frame can support me seemed kind of surprising. But as I started to dig further into it and actually work out the numbers, it became clear to me that it's not so crazy. So let's jump in and I'll show you how I would analyze this as an engineer. So the first step when we're dealing with any kind of engineering problem, for me at least, is to draw a picture. And in this case, it's going to be the free body diagram, which is just a simplified picture of whatever you're analyzing. So in this case, instead of the complex pull-up bar that I just showed you, I personally would just draw this as my simplified shape, my simplified picture. So this is a side view of the pull-up bar. This is where it would hook onto the door frame, and this is where it would contact the other part of the door frame, or it's also where you hang from it. It's where the actual bar would span the door. So start with our picture. It'll also create our coordinate system, which will make things easier. So we'll say up is positive for y and right is positive for x. So body diagram, coordinate system, and now we can start adding our supports and forces. So for any engineering problem, you can represent supports in different ways. So there are three primary types of supports that we can deal with. There's fixed support, which we represent by a line with some slashes. We have a pinned support, which we represent with just a triangle, and then we have a roller support, which is a triangle with some little rollers under it. So a fixed support is as if you were going to weld something. If you weld it, it's not going to move up or down or move really at all. It's fixed, and it's not going to rotate either. So it locks down pretty much all the degrees of freedom. So that's the most restrictive. Then we have a pinned support, which is what it sounds like. If you were to put a pin through something, it would let it rotate, but it would keep it from moving up and down or left and right. So we lock down our X and Y movement, we'll say. So less restrictive than fixed. And then roller is the simplest type of support. That's as if you were gonna set something on the ground, for example, where it's supported vertically, but if you pushed it, it would move freely. So the least restrictive. So in this case, we can start applying our supports to our problem. So our first one will be where it hooks onto the top of the door frame, which this would be a pinned support, because when you hook it on, it's able to pivot around that top point. Top door frame keeps it from moving up and down, and then you have the wall, which keeps it from moving at least inward. So we have that, and then once you hook it and it swings down, you have the other part of the door frame, which is really just a roller support in this case. I'll draw that here, because it'll keep the pull-up bar from wanting to move inward, but it's got no restriction up or down. So for this problem, those are the supports, and then the only other thing we have to add now is our external force, which is just you hanging from it. So in this case, I'm just going to draw an arrow down and say F. So this is the basic setup for the problem. Like, you've drawn your picture, now it's just working out the math. So in practice, instead of keeping these triangles in here, we instead replace them with arrows, just like you saw for my force. So like I was saying down here, the roller support really only keeps the pull-up bar from moving, well, I guess in this case, inward. So we'll just draw an arrow out, and the direction of the arrow doesn't really matter. Like, as you work through the math, it'll tell you if the arrow is facing the wrong way. And the arrow in this case just represents the the reaction from the door frame. So, and we'll call this RT. T for trim, the trim of the door, that's where the pull bar technically rests on. So it's only got a force in one direction because it's a roller support. And our pin support has forces in two directions. Like I was saying, it's restricted vertically and inward by the wall. So here I'm simply just going to say RY and RX. This is more so the picture you would start with. With this, you have enough to solve the problem. One thing I wanted to mention is that I actually measured these distances on my pull-up bar. So if you're looking at it from the side like this, which I don't know if this is a great view, this is actually a square. Like if you were to draw imaginary lines through here. And in this case, the distance from this support to the force is 7 inches, and the vertical distance from where it contacts the trim to our pin support is also 7 inches, which that just makes things easier when we get to the math. So with our free body diagram now completed, we can start applying the equilibrium equations. So anytime you're analyzing something that's not moving, you can apply these equations. And they are the sum of the forces in the x direction equal to 0. That's a sigma sign, that just means the sum of. We have the sum of the forces in the y direction are equal to 0. And the sum of the moments equal to 0. So these say that it's not translating, it's not moving up and down or left and right, and the moment is saying it's not rotating at all. So like I said, you can apply these anytime you're analyzing something that's not moving. Like for example, I have a ball in front of me. Since the ball isn't moving, really the only one of these equations that has any relevance is this one, because it's supported by the floor. So you have the weight of the ball, and there's just an equal opposite reaction, which is one of Newton's laws. And then the other ones are just can be canceled out. So starting with these equations, we can look at our free body diagram and just start completing them. So instead of saying the sum of the forces in the x direction, I'll literally say Rx plus RT equals 0, something like that. And I'll work that through for all three equations. So starting with the first one, like I said, if we're saying right is positive, we have, oh, that's a terrible R. We have Rx plus RT equals 0. It's our first equation. Then for the sum of the forces in the y direction, we have Ry and F. So in this case, F is down, so we'll say Ry minus F equals 0. And this is where it helps to have your coordinate system listed out. I could even draw a little plus here and there, so you know. This just helps you from messing signs up. So, and then the last one is the sum of the moments. So you can take your moments about any point you want to, but certain ones make your life easier. So for example, I could just pick an imaginary point here and say, okay, the moment, or a more intuitive way to think about moments is just calling it torque. So we have a force at a distance. So in this case, I would have an imaginary line going to this force, and so on, but it gets complicated. So we can be a little smarter about it and pick a better point, which will make our lives easier. And in this case, I'm going to pick this point right here. So since I'm choosing this point, there's no moment created by the reactions here, since there's no moment arm. You need some kind of offset to create a torque. So that immediately eliminates two of my variables. And if I'm going here, the only things I have are F and RT. So at 7 inches for both of them, really, We have the force creating clockwise torque, and we have RT creating a counterclockwise torque. So to make things even clearer, I'm going to say clockwise is positive. So from here, we'll have F times 7 inches is positive, and we have RT times 7 inches is negative, equals 0. So those are your equations, and that'll help you solve for all the unknowns. So what's nice about this case is that the number of equations, we have 3 equations, matches the number of unknowns. We have Ry, Rx, and Rt, and whenever that happens, whenever those numbers match, the problem is statically determinate versus being statically indeterminate, which is a little harder. You have to start making assumptions or pulling other information to help determine the unknown values. So it works out nicely in this case. And if you go through here, and I'll work it out explicitly just to make things extra clear. But if we look at them and start rearranging, we'll notice that all of them are equivalent to each other. So for example, if I'm looking at this, I know Rx has to be equal to Rt or negative Rt to satisfy this equation. Like you would just move that over to the other side. So from our first equation, we can simplify it to this. Rx equals negative Rt. So that's just telling me that one of these arrows is wrong, and you could flip either of them, it doesn't really matter. From the second equation, if we move F to the other side, we see Ry equals F, which makes sense because they're facing opposite directions versus my horizontal forces were the same direction. So that was telling me they have to flip. So that's the piece of information we learned from the second one. And from the third one, it's nice since both of these values are the same. So we ultimately learned that F equals RT. If we were to move that to the other side, the 7's just cancel. So looking at these equations now, you could follow that F equals RT. So these values are the same. F also equals Ry. So these values are the same. Sorry, these values are the same. And we see that since F is equal to RT, F is also equal to negative Rx. So overall, all this tells me is that all of these values that we don't know yet are equivalent to the force, which is my body weight. So this is going to be, in this case, 180 pounds. This is 180 pounds, and this is 180 pounds. It just happens to work out nicely. And while I'm at it, just to make my life easier, I'm going to flip the direction of one of these. Okay, so now I'll basically summarize what I just said at the top here by saying F equals RT equals Rx equals Ry. So it's super nice and easy. And I'll even say, just so we can start assigning some actual values to things. Okay, so what is this telling us? If we're looking at the free body diagram, basically I know since all of these are the same value, the door frame really is taking my full body weight. If we ignore friction, which there would be some friction for where the pull-up bar is pressing into the wall at the top and the door frame at the bottom. But the friction wouldn't be a whole lot. I don't know exactly what the coefficient of friction value is, but the pull-up bar in my case just has foam. So you have foam on painted drywall, and then down here it's electrical tape on painted drywall. So there is a little bit of friction, but it's not going to be a ton. Like if you say maybe it's 1/10 of the value of F, which in this case would be a coefficient of friction of 0.1. You would get 20 pounds of vertical support from that friction here and about 20 pounds from the vertical friction here. So in that case, that only saves you 40 pounds total. So the door frame is still supporting well over 100 pounds in this case. So as an engineer, what you would do now is start to work your way through the system, so to speak. So in this case, if I draw out the door frame, I guess that was kind of a weird way to draw this, but this is the same as this. So as you saw, there's a whole bar that goes across the top of the door, which would make it a distributed load like you see here. We draw that as a series of arrows next to each other. But we have our full, in this case we'll ignore friction and say full 180 pounds on the top of the door frame pressing down. So if I were to analyze this, I would go piece by piece and start with this piece here, that top part of the trim, and then if that piece survives, I'll say, then I would look at the side pieces, and that's exactly what we'll do. Okay, so our top piece. So since it's cut at an angle like this, we really have a normal reaction at each side. So although these are at angles, we know that vertically it has to support that full force. So if we say this cut is at 45 degrees, we would do our static equilibrium equations again. In this case, I'm really only concerned about the vertical, since the x's would cancel. They're trying to squeeze that top piece of trim, but that's not as important. So if I were to write out just that vertical equation, I would say, and we'll just call this R. So in this case, I have two of them. So I would say 2R times, in this case it would be the sine of 45 degrees. 2R sine of 45, and we'll say minus F, since it's facing down, equals 0. So from here, we know that So from here, we know that R is equal to F, if we rearrange this, over 2 sine of 45. So in this case, if F is 180 pounds, we get, I gotta do math, I don't know. Okay, so R is about 126 pounds. So to explain this sine of 45 a little bit, because you might have no idea where that's coming from, anytime you have a force at an angle, like we have here, we have that R at 45 degrees with respect to horizontal. So anytime we have a force at an angle like this, it can be broken up into an X and a Y, if that makes sense. So it's the same thing as having an X force plus a Y force. So when you're dealing with a right triangle like this, taking the sine, and you'll see sine on your calculator, taking the sine of whatever angle this is will give you this value, and then taking the cosine of 45 would give you this value. So in general, if you see a triangle like this, sine I think vertical, cosine I think horizontal, but I'm only dealing with vertical here, so I took sine of 45, and that ultimately gave me my answer of 126 pounds. Okay, so we've solved for our R. So what is this telling us intuitively? So just looking at it, we know that since the forces are at an angle, it's going to want to kind of bend that piece up. But assuming that the piece doesn't move, we can really start to look at the next piece, because the side pieces of trim that I erased are what this piece would transfer all of the load to. So since we solved for our reaction here, we can then erase this and now draw just our side pieces. I'm just going to draw one side piece to make things simple. So if we have our side piece of trim, you have an equal opposite force pushing into it of 126 pounds. So again, just thinking intuitively about it, if we have a force at an angle on this tall piece, we have some component of that R which is going to be pushing down, and then another component which is pushing out. So you can imagine if this piece wasn't supported very well, it would want to bend out like that, bend out and compress as well. So we really just have to look at the failure modes of this piece of trim, which, thinking about it a little bit, the ones that I came up with are the trim could buckle. Since it's a long skinny piece, if it weren't supported along the length very well, you would see it want to flex out, and you could imagine it snapping, long skinny piece. If it doesn't buckle like that, it would want to shear the nails you put through it. So when you install this trim, there's a bunch of tiny nails you use. They're skinny nails that go through. So every few inches you would hammer one of these through the trim. So we have buckling, we have shear. Technically, like I was saying, it would want to bend out if it wasn't supported well. Since it would want to bend about its stronger axis, I don't see that as much of a problem. Plus, there's so many nails through it that it wouldn't really want to move anyways. So if I were designing this pull-up bar, I would probably make the assumption that this trim wouldn't touch the ground, because you don't know how somebody's going to install it. Ideally, it would be placed perfectly on the ground and your nails wouldn't want to be put into shear, but you can't necessarily assume that. So assuming it's not contacting the ground, all of your nails throughout the length are what's supporting your full body weight, which makes sense. So the last step to this problem would be to just analyze the nail brad itself, wire brad, trim nail itself, and calculate what the minimum number would be. So we need to analyze those. So my last piece here would be to probably look at a side view of the nail. So if we assume this is our wood behind the door, and this is our, so we're saying this is fixed, this is the wood that the nail is in, and this is our, let's say, trim. We have what would be 126 pounds, as you saw previously. This would technically be at an angle like I was showing, but we would have another distributed load, and I'm just gonna write the actual value instead of the variable just to make it clear. So this 126 pounds wanting to break this trim nail, it's gonna want to shear it as you're pushing down on it like I was showing. It's gonna want to rip through the cross section of the nail, but it's also technically going to want to bend it a little bit. So I don't know off the top of my head if the shear or the bending is worse for these nails, but you could imagine if the trim wasn't installed snugly against the wall around the door, it would want to bend the nail even more. But assuming it is installed pretty flush, the bending stress here would really be created by the force at the half thickness of your trim. So in this case, for shear, so we can compare and see which is worse, we have 126 pounds divided by, and actually look this up real quick, the area of one of these nails is 0.002, I think, 3 inches squared, which gives us a stress of approximately 54,000 psi shear stress. So typically the smaller diameter nail or bolt you use, the stronger it is. So in this case, I think I was seeing that the yield strength of one of these trim nails is about 100,000 psi. So in this case, it seems like one of these nails could support it if it was purely in shear. But we also need to check bending. And so our equation for bending isn't quite as simple as the shear, where the shear is just force over area. The bending is the equation my over I, where our moment would be the 126 pounds times the half distance, because you can replace this distributed load with just a load at the center of like whatever piece of trim you have. So just for simplicity, I might put that there. So you have the distance to that arrow and the times the force to give you your moment. So that would be 126 pounds times, we say the trim is about a 1/4 inch thick, we have times 1/8 inch thick. I'm running out of room here. Our Y would be, if I draw a dashed line through the center of that nail. So whatever, in this case, cylindrical object you have in bending, the Y value is the distance from that centroid to the outer portion. That's going to be where you have your maximum stress. So in this case, if the trim nail is about a 1/16 of an inch thick, a little less, I think I googled it and it was 54 thousandths, something like that. So we'd say 27. So I'm running out of room, but that would be times 0.027. And then our I value is our cross-sectional moment of inertia. So it's how resistant your shape is to bending. So for something like a cylindrical nail, it's the same in all directions, but if I take something like a book, different ways I orient it will make it more or less resistant. So you can imagine if I tried to bend this book like that, it would bend pretty easily. If I rotated it like this and tried to bend it, it would be highly resistant to any kind of bending. So in that case, the equation for cylindrical shapes against bending is pi d, the diameter, to the 4th power divided by 64. So in that case, we get something very, very small. So just working through it like that makes me realize that this is for sure going to be a bending dominant problem. And there's some argument that could be made that maybe this force isn't exactly at the middle of the trim. If this force were to be closer to the wall, there would be no bending and it would be a shear dominated problem. But I believe putting a force through the center of the trim is a reasonable assumption, because it really would be a distributed load like that through the thickness, I would think. So if we solely focus on bending now, just to make our lives easier, I'm going to erase some of this, free up some space. Okay, so working through it this way, we said we have 126 pounds. In this case, we're just going to look at one nail first, and then we'll factor in how many nails there are. So 126 pounds times, we said that was at an offset of an 1/8 inch approximately. And maybe even that's too large. I'm gonna double check that. All right, so an 1/8 is actually kind of small. I was measuring at the trim. The trim is actually skinnier on one side and fatter on the other. It goes from like 1/4 to 1/2 inch. So in this case, instead of 3/8, that would be 3/16. And then we have the distance from our centroid to the outer portion, which is 27 thou. And then, as I was saying, for our shape resistance, we have pi over 64 times our diameter to the 4th power. So this gives us a stress of approximately 1 1.5 million PSI. So that sounds like a lot, because it is. So I googled the yield strength of one of these nails, and it was about 100,000 PSI, give or take. Like I said, they're pretty skinny. If we say each nail can support 100,000 PSI, we'll just say 1E5 PSI. That tells us we need approximately 15 nails. So 15 nails is completely realistic. Like, you have two sides that are approximately 7 feet tall. So if you just place one every 3 inches or so, we'll even be generous and say place a nail every 6 inches. That's about 15 per piece of trim, which is totally realistic. The ones on my door frame are even closer than that. So just using that logic, we can see if we continue with our assumption of 6 inches apart per nail, and we have 15 per, that's basically the same thing as saying I can support approximately double this value, 360, which I think is around the rating. It might even be lower, like 250 pounds. But I'm sure that's with some margin built in by the designer. But yeah, this is the physics of the problem, and shows you that it's completely realistic and doable as long as the trim is installed reasonably. So all right, thanks guys. This has been a long one. Appreciate it.